So far we've seen that the stabilized methods for an advective term can be motivated from the perspective of a fine scale model. So these were SUPG, streamline upwind Petrov-Galerkin, and GLS, Galerkin least squares. So it's a natural thing to now ask whether the stabilized method for the pressure stabilization can also be motivated as such. So that's what we'll do in this video. And naturally, that's a stepping stone for being able to treat the Navier-Stokes equations, which are a combination of an advective term and this Stokes pressure pair. So we're going to have a look at the Stokes problem first, and we'll see that pressure stabilized Petrov-Galerkin and least squares and incompressibility constraint also kind of come from a variational multiscale decomposition. So what was the Stokes equation again? And I'll already write it in a weak form. So we're trying to approximate. Well, let's actually just start with the original formulation. So we have the weak formulation of the Stokes equation. And it looked like this. We're trying to find a solution U and a solution P in two spaces. A space for the velocities as H10, a vector valued space, so D of those as the dimension of the physical space, and a pressure space, and the pressure space could be L2. And we're looking for the solution U and P such that for all test functions V and Q, also in H10, D, and L2. So blending into my video here. D cross L2. Okay, I suppose that's clear. We have the following weak statement: nu times gradient U, comma gradient V minus the divergence of U, comma PH is equal to F, comma V. And these are all L2 inner products on the domain omega. And the second line was sorry, this is a V. The second line was that the divergence of U, comma Q was 0. So this is the weak statement of the Stokes equation. And the finite element formulation that we've looked at is the one where we simply now add discrete versions of our solutions and also of our test functions. So no longer H10, but maybe some VH, and no longer L2, but some QH. And then we looked at this formulation and we saw that the properties of the solution, the quality of the solution depended on our choices of VH and QH, not independently, but rather their combined use. So certain combinations of VHs and QHs gave either locking behavior or spurious pressure modes. From the variational multiscale perspective, we now understand that this kind of comes from the fact that we've dropped out all these U primes and P primes. But what we're not going to do is trying to fill in those U primes and P primes. So what we're going to do instead is going to look at the formulation that we are using, the finite element formulation, so this one. And we're going to deduce what kind of projector this implies. We've talked about this before, that the standard finite element method already implies a certain projector, one that was actually very good for symmetric problems, like the ones that we obtain in linear elasticity, because the projector that we obtain is then correspondent with some sort of an energy minimization, and or we say that we get the best solution in the energy norm, and that was the Galerkin orthogonality projector. Yeah, so if we throw away all these u primes and p primes, then what we're implicitly saying is that the following needs to be true. So there should be a gradient here. Excuse me. Yeah. That the following needs to be true, that these weak statements need to hold. This has to be true for all VH in our space, or discrete approximation space. And this one has to be true for all QH in our approximation space. So rather than saying that our choices of elements are somehow inappropriate, what we could also say is that our choice of projector is somehow inappropriate. And this gives us a different angle of trying to solve this problem rather than trying to shuffle around our choices of velocity and pressure spaces. What we can do instead is try to change this projector. And we can take a short look at this projector because it's really not that bad of a projector per se. It is symmetric and it encodes sort of a minimization problem by itself. We saw that these mixed formulations, these saddle point problems, correspond to constraint optimization problems. So this is somehow an optimization of our solution UH as sort of a minimization, but also with a certain constraint. And okay, apparently that does not work particularly well for certain choices of finite element spaces. But we can try to fix that. We have, well, I'll just write this down explicitly. We have two ways of trying to fix this problem from the variational multiscale perspective. The first one, okay, let me write down some of my thoughts at this point. So apparently, this Galerkin orthogonality, getting ahead of myself. Projector is not suitable. So we have two ways of trying to solve this problem now. We either change the spaces VH cross QH, or we change the spaces V prime cross Q prime. Now, how do we obtain these fine scale spaces? They were the kernels of the projector, the kernel of this projector right here. So all the functions U prime comma P prime such that this is indeed true. So a different way of saying that we're going to change the fine scale space is to change the projector. Yeah, so the change of spaces VH cross QH is something that we've tried. We looked around for stable pressure velocity pairs, and now we're going to try and do this differently. We're going to change the projector. So what can we do to change this projector? Well, I would say we're going to add some sort of weighting, some sort of either L2 weighting or some sort of H10 weighting, some weighting on the error that is coercive and symmetric. So I'll copy this over. And I'll add a weighting both on the Q and on the P, both on the P and on the velocity, so both on the velocity and on the pressure. And since we know that, well, L2 weighting was not particularly beneficial, right? Because this would introduce these oscillations near sharp layers. We're gonna do instead, what we're gonna do instead is add weighting on derivative quantities. And for the pressure, this is well, precisely the H10 weighting. Yeah, so we're gonna add some factor, let's call it beta, of the gradient of P, comma, the gradient of Q, and then P prime and QH. Remember, this corresponded to the projector, the H10 projector for a scalar field. Let me scroll up and see if we still have that somewhere around here. I think, yeah, that was right here. So if we take the gradient of our scalar field and the gradient of our test function field, that corresponded to the projector of minimizing in the H10 error. So that's what we'll add as well for our pressure field. And well, our velocity field is a vector. What we could do instead is add maybe a weighting on its divergence. We also know it has to be divergence free, so that doesn't sound like a terrible idea. So I'll add alpha times the divergence of U prime, comma, the divergence of VH. And in both cases I make sure that it's symmetric, and it's at least a semi-known quantity, in the sense that if we substitute the same thing in both slots, that it will always be positive. Yeah? Because with those properties, it kind of corresponds to a minimization problem, in the sense of an error minimization. So I'm adding two quantities to my projector that are, again, symmetric and positive definite, or at least positive semi-definite. And we have now also two parameters, alpha and beta, that we can play around with later and kind of tweak the behavior of our core scale solution, or at least what the core scale solution is going to look like for any possible true solution. And we can tweak that now based on alpha and beta by changing the projector. But to do this, we first have to make this show up in the finite element solution. So we're going to use this projector inside of our finite element solution. And if we did not have these red terms, then that ended up just being the same thing as crossing out all these fine scales right here. So now that we have these red terms, we can more or less look at this as if we substituted the red terms in place of these white terms. So we would get, in place of these red fine scales here, we would now get these two red terms. No, this one and this one. Okay, so let's try and work that out. Okay, I'll be a little bit more careful with my coloring now. So we're going to change this to a finite element formulation. So we're looking at the core scale problem. So we're looking for UH and PH in our core scale approximation spaces VH and QH, such that for all VH, QH in VH and QH. And these become H's as well. And now effectively we have cancelled all these fine scale terms, and in our new setup we have replaced those fine scale terms by what this projector is saying. So we have to now include these red parts. Yeah, so let me state this very clearly for the second line. So this should be reading a divergence of U prime, comma, QH minus minus. But here we're seeing that this minus Q prime, minus U prime QH corresponds to beta gradient P prime gradient QH. So I can actually replace this one by minus beta gradient P prime comma QH. Gradient QH, there we go. Same thing for the first line. This should have said all these fine scales in here as well, but those fine scales, those are these, so I can replace that by that, and that means that our equation is now going to include another term, minus alpha divergence u prime, comma v divergence vh. Okay. So this would have to end up being our finite element formulation, but now we still have some of these fine scale quantities in there, right? The u prime and the p prime. So we have to treat these somehow. We can either substitute a fine scale model for those, or we can do something a little bit more immediate, something more exact, because we actually know quite a bunch about these fine scale quantities. If we take a look at what the actual Stokes equations would say, well, then we know that the divergence of the solution u is going to be equal to 0. And that is now the divergence of our coarse scale plus the divergence of our fine scale. Well, I'm precisely interested in the divergence of my fine scale. So I can from this actually already obtain that the divergence of my fine scale is going to be equal and opposite to the divergence of my coarse scale. Yeah, so that's already immediately what I can substitute in place of that. So that's a direct closure of that fine scale occurrence, rather than having to substitute some sort of model in there. Can we do something similar for this gradient of p prime? Somehow yes, but not quite as direct. We have a gradient of u prime, or a gradient of p prime also in the momentum equations. Those said that 2 times nu of the Laplace operator on u, so this is the vector Laplacian, plus the gradient of p was going to be equal to f. So we'll separate the scales here. So this is going to be the same thing as minus nu Laplace of UH plus of U prime PH P prime, and thus minus nu Laplace of U prime plus gradient of P prime is equal to F minus or plus nu and that's actually precisely minus the residual. And so this is pretty much the same thing as what we realized earlier. The fine scale equations, they can be interpreted as being forced or driven by the residual of the coarse scales. Now we needed this gradient of P prime, and that actually ends up being then minus R plus nu Laplace operator of U prime. So I can substitute this in there. So it seems like we're not really getting anywhere because we still have this fine scale of the velocity. But let me zoom into that particular term then. So we have minus beta times minus the residual, so that's going to be a plus, comma gradient of VH, no, gradient of QH, sorry, minus beta nu delta U prime, comma gradient of QH. But if we do integration by parts on this one, and we do this element-wise, then we end up getting like a third order operator on QH plus a bunch of element boundary terms. And now we already sort of approximate that on the element boundary U prime is equal to 0. So we're going to cancel a bunch of those boundary terms. And in fact, what we're going to say is that this one is approximately equal to 0. And again, if we do integration by parts, then we'd get a third derivative of q, if q is either just linear basis functions or quadratic basis functions, that the interior is actually going to be identically equal to 0, and you would only have these boundary terms. So at that point, we make an approximation by saying that this is approximately 0. But yeah, at some point we have to make approximations. So this second occurrence of a fine scale, the gradient of p prime, we're going to replace that simply by beta times the residual, and I should say the residual of the momentum equations, just to be a bit more explicit here, because we have two equations, a momentum equation and a continuity equation, and this is the residual of the momentum equation. So if we do all of that, then I can copy over my finite element formulation once more. And then we get a closed relation, or a relation that is no longer dependent on fine scales. But we now have beta times the residual. We have alpha times the divergence of UH and a plus. And there we already have it. This is precisely the LSIC term right here. We call least squares on the incompressibility constraint. And this is precisely the PSPG. The pressure stabilized Petrov-Galerkin term. So we have to, of course, also technically we have to write this as the sum over elements, right? Because the residual in the strong form is only defined on the element interiors. You can also define it in a global sense, but then you get into some technicalities. You would have to interpret certain integrals in the sense of distributions, and it gets again a little technical. In our model, we would only look at the element interiors. So this is a somewhat different approach to this fine scale modeling and a variational multiscale method and its connection with stabilized methods than the one that we took before, because we hardly introduced a fine scale model here. What we did is we changed our projector in such a way, a smart way, such that we end up with fine scales that we can actually treat quite effectively without having to do too much modeling. In this case, the modeling is only just ignoring this second term here, which actually does have a lot of zeros in there, so it's not a huge assumption. At least that's something you would actually have to verify, but it's not a crazy idea, let's put it that way. So it's I would say somewhat of a different way of looking at things, but also very it gives a fresh perspective on things, because now we understand that these stabilization parameters for the PSPG and LSIC method, well, they're not necessarily immediately linked to the modeling of the fine scale, but they're immediately linked to the definition of our projector, right? The one that we have right here. And you can rewrite this a little cleaner. You can actually rewrite this into also a constraint minimization problem. And then we see that, well, we added some elliptic terms to this minimization. So some terms that make it the minimal better defined or cleaner. So that's my way of explaining also LSIC and PSPG from the perspective of the variational multiscale method. And so now we have the advective term covered and these two terms covered, and then we're finally ready to actually look at how this would show up in the Navier-Stokes equations and how to deal with the nonlinear term. And then we're gonna see that makes perfect sense also from the perspective of a turbulence model, and that kind of ties everything nicely together. And so that's what I'll do in the next video. So thank you for your attention.